All right, time to learn about logarithmic functions. So you know how we always introduce new ideas and then we introduce the inverses? Well, logarithmic functions are inverses of exponentials. So that means that graphically, again, if we draw an exponential, so let's just use like y equals 3 to the x as an example. That's going to graph through 0, 1, and 1, 3. Looks something like this, and it's got an asymptote at y equals 0. I'm going to do this in orange. So here's your exponential, and you've got your asymptote at y equals 0. 0, 1, 1, 3, y equals 0. These are your starter points. Well, the inverse of that is going to flip over the line y equals x. That's how inverses always behave. And so that's going to end up looking like this. And what's interesting is the asymptote also gets flipped over that yellow line. And so when it flips over diagonally over that yellow line, it actually becomes vertical. And this pink graph that results is a logarithmic function. And the way we write it is y equals log base 3 of x. That's the equation of the pink graph. Now, so first of all, this 3 is a base. It's a subscript, okay, underneath. It's not log 3 times x. It's a subscript of 3. And it's the inverse function of this exponential. Now, why 3? Because the base on this exponential was 3. So just like the base can change on an exponential, the base can change on a logarithm. And it can be any number, including e, which we'll talk about in a second. So how do you find inverses of functions? Well, you switch your x and y and solve, right? So if the x and y values switch, then that means that all of your starting values, x and y, also switch. So for a logarithm, the start values, instead of 0, 1, they're going to be 1, 0. Instead of, in this case, 1, 3, it's going to be 3, 1. And instead of an asymptote at y equals 0, it's going to be an asymptote at x equals 0. Now, it's really easy to get these mixed up because they're the same points, only flip-flopped. So it's really helpful if you memorize the general shape of a logarithm. A lot of people, just like they feel like an exponential might have a vertical asymptote, they also feel like a logarithm should have a horizontal asymptote, and it doesn't. This part of the pink graph is growing up and up forever, very slowly, but it does grow up forever. So that means, just like on the exponential, the domain is all real numbers. Now here, down on the log, the range is all real numbers because the x and y's flip. So the y values, this pink graph is going to cover all y values going down, and then this part is going up and up forever. And so all of these y values on this axis meet up with the graph at some point. The domain for these is going to be either the asymptote to the right, or the asymptote to the left, just like the exponential was that way for the range. So everything's flipped, and what you're going to do in this section, first of all, is be able to graph these. So let's do some of those. And the graph shifts, this is the third time we've heard this lecture, the shifts work the same way. So if I have just a basic, let's say log base 2 of, I'm going to put an x here. Here's where all the stuff can go. You can have a negative here, and that negative, if it's out front in front of the log, is going to flip you down over the x-axis, just as it always has out in front. You can have a negative in front of this x, and that's going to flip you over the y-axis. You can have a plus or minus a number in with the x, and that's going to shift you left or right opposite the sign. And you can have a plus or minus a number tacked on the end, and that's going to go up, down, same sign. So that's all the things that can kind of go wrong, if you will, with a log. And let's try to draw a couple. So y equals negative log base 4 of x plus 2 minus 3. So the first thing is you need to memorize your start points. Put those on a note card. For a logarithm, you're going to start at 1, 0 and B1, whatever the base is. I'm using B for this number right here. So in my example, I'm going to start at 1, 0 and 4, 1. And there's an asymptote at x equals 0. So here's my start graph, my asymptote, and it looks like this. Okay. We want to do flips before shifts. So my next thing is to look in this spot right there and this spot right there for a minus sign. There isn't one in with the x, but there is out in front. So out front, we're going to flip down over the x-axis. So that's going to look like this. Again, if you have trouble drawing that, take your paper and fold it on the axis that you're flipping over, and then pretend like the ink is wet and where it imprints is where your new drawing should be. Okay, so that's flipped, and then we're going to take a look at our shifts. This is in a number in with the x, so that's going to be right and left opposite the signs. So because that's a plus 2, we're going to go left 2. And this number tacked on the end, and it can be on the front as well, is a negative 3, so we're going to go down 3. So I'm taking this pink graph, and I'm taking care of my marked points, my starting points. Those are the ones that I'm going to be looking at to be accurate on your drawing. And you're going to go left 2 and down 3. Left 2, down 3. And the asymptote also goes left 2, down 3. Now left 2 puts it here, but moving this line down just moves it onto itself. So the downshift doesn't actually move the asymptote in a way that matters or changes the picture, but the left-right does, which is, if you remember, opposite of the exponentials, which makes sense. And then I'm going to draw this just like the pink graph, only a rigid shift. And this is my final graph. Okay, let's do one more. Then we'll talk about a couple properties of these things. Okay, what I would do with this is I would pause the video and I would try this on your own and see if you can graph it. Oh, sorry, I need to put a base here. Let's put a 2 there. Okay, see if you can graph it on your own. All right, start position. You should have had 1, 0 and 2, 1. This is your start with your asymptote at x equals 0. Okay, I have these memorized. These were on a note card at one time in my life. I memorized them. Then I'm looking for a minus sign for a flip. The minus sign will be here, right in front of the log, or here, right in front of the x. Since there's not one in front of the log, it's not going to flip down. This one is going to make it flip over. So I'm going to take both of my dots, flip them over, and draw the symmetric graph on the left. There. And then I'm going to do shifts. There's no shift inside here with the x, so there's no left and right shift. There is, however, a shift here. Now that's That is an up and down shift because it's hanging out on its own. It's in front. It can be in front or in back, but it's not attached to the log with multiplication. So this is going to be a down 3. So I'm going to go 1, 2, 3, 1, 2, 3. And this asymptote is also moving 1, 2, 3 down, but that just moves it down onto itself, so it doesn't actually change position. And the green graph is your final answer. Okay, let's talk about domain and range of these. Let's go back to the first one right here. Domain of the orange graph, it's going to be the asymptote right or the asymptote left. So here's the asymptote, and my graph is to the right of it. So that means it's going to be a -2 to infinity, and the -2 is an asymptote, so we get round brackets. The range is always all reals on these guys, and you can see that with the orange graph. It's covering all the y values, all the way up, all the way down. Down here on the green graph, the domain is the asymptote, which is 0, and it's left of there. So the domain is going to be -infinity to 0, round brackets, and the range, oops, I always want to do a double bar on the range. Range is all reals. Okay, good. Now let's talk about some other unique things about logarithms. First of all, shorthand notation. If I write a log without a base, that is shorthand for log base 10 of x. So a base 10 logarithm shows up often in nature, and it shows up so often that we shorthand it by dropping the base. And so there will be some of those in your homework. It'll just say graph log of x, and so that means that your start point for your graph is going to be at 10, 1. Okay, the other shorthand is we write this. The way we say this is the natural log of x. That's what this is. And sometimes we say shorthand lnx. Okay. And what this is shorthand for is a base of e. This is what it means. So when I ask you to graph the natural log of x, your start values for it are going to be 1, 0, and 2.71. You're going to estimate that. Again, if you want to write it like this, that's what you're graphing. Okay, but everything else is the same. So anytime you see E, you can just think 2.7 and be good. Okay. Okay. Now, logs have a unique ability to transform their shape algebraically. If I have a standard log, let's just call it base b of x, I can write this algebraically in a different way. And the way that it translates is the base to the power of what the log is equal to equals what you're taking the log of. So here's how I see it in my mind. It's the base to this power equals this. I kind of think of it as a circle like that, starting with the base, and that's how you can rewrite it. Now, what's a little bit weird about this is not an exponential, it's a logarithm because the y is in the power. And so it's in what we call exponential form, but it's not like you're making it into its inverse. It's just changing form into an exponential form. And why that's an advantage is when I ask you, like, what's the log base 2 of 4? What is that? This is a number. What is that number? And you would say, I have no idea. Okay, but if I could write it in an exponential form, you might be able to look at it and tell me what the answer is because we understand what exponents are. So sometimes where we're going with this is we're going to eventually solve logarithms. And so sometimes it's valuable to rewrite a log into an exponential form and take a look at it there. Okay, so for example, let's say I go y equals log 2 of 9. And I want to know what y is. So basically, what is log 2 of 9 equal? And so I don't know in this form, but if I could rewrite it in an exponential form, I might be able to. So here we go. It's going to be 2 to the y equals 9. And I messed up this example. I meant to write a 3 here. So can I change that? Sorry about that. There we go. I was thinking backwards in my brain. So I'm writing 3 to the y equals 9. So 3 to the y equals 9. Now look at it. What does y equal? Okay, if you think about it, well, y is going to be 2 because 3 squared is 9. So that's the idea of sometimes it's not clear what this is in this form, but if I can rewrite it in an exponential form, sometimes I can eyeball it. Now, sometimes you can't. All right, let's go back to, I made a mistake because I meant to put 3 there. Let's go back to my original problem and let me show you why I wanted to change it. If I rewrite this in exponential form, I go 2 to the y equals 9. So 2 to the y equals 9. What's y? Well, I don't really know offhand. I mean, it's some decimal or fraction, right? Because 2 is not an even power to the 9. So these problems, if you're going to be able to eyeball it, kind of have to be just right. We're going to learn other methods to solve that are a little bit more fluid and widespread than this, but this is kind of our starting place. All right. So on your homework, what the directions are going to say is they're going to give you some kind of log. So y equals log base 4 of 16, and they're going to say rewrite this in exponential form. And all they want you to do is use the little algorithm to put it into the different forms. So 4 to the y equals 16. Okay, if they ask you to solve it, you can, but I think the homework's just asking you to get practice rewriting. And then they're going to do it backwards. They're going to give you something in exponential form and say rewrite in logarithmic form. So if I give you this, then you're going to rewrite this as, okay, this is the base of the log. This is what I'm equal to, and this is what I'm logging. And just getting practice going back and forth between those. Okay. In addition to that, there are some properties of logs that you should memorize. I would put these each on a note card. So on the front, I would say log b of b to the x. And then on the back, I would put this as what this is equal to. Now, before I tell you what this is equal to, let me tell you that we started this by saying that logs and exponentials are inverses of each other, specifically logs and exponentials that have the same base. So for example, log base 3 of x is the inverse function to 3 to the x. These guys are inverse functions of each other. And the way that they work is in composition. So if you take this and plug it into the log, then they cancel each other out, which is what you're looking at in this property right here. This is a log of a base composed with an exponential of the same base. And what happens is these guys cancel and it just leaves the exponent, but the exponent comes down to ground level. It's a very interesting property. So anytime you see like log 3 to the 5th, that's just 5. That's what that equals. The log and the base of the exponential cancel out, and the exponent comes down. And the reason you want to memorize these properties is because I'm going to expect that as we step into solving equations with these things, that whenever you see these, that you're reducing, so to speak. It's kind of like, you know that this reduces to this, right? And we want you to recognize reducing. And this is one way that logs reduce. Okay, so this is the first property. The second property is similar, but the other way around, because remember inverses, you don't just have to plug this into this. You also can take this log and plug it into the exponential. So what that property looks like is if I have a base and then I've plugged the log into the power and it's got the same base, then these guys also cancel and the x comes down front. Okay, so for example, if I have 5 to the log base 5 of 7, that's just going to be 7. These guys cancel. Okay, I know this can feel weird. Especially if you've not seen logs before, this can really feel foreign. So just stick with it and do the practice, and I think you'll start to catch the hang of it. The other rule that I want you to know is that the log of any base of 1 equals 0. Now, why is that? Well, let's remember what the log looks like. What's my start value? 1, 0, right? Oh, there it is. This is your x value. This is your y value. So the log always looks like this, right? It's always going through that point. So anytime I have the log of 1, then that y value, corresponding y value is going to be 0. Okay, those are the 3 properties that I want you to know. Now, these properties hold for all values of b, including e. So what I'm going to do is I'm going to put on the right, I'm going to put these partner properties. So this is like 1b, okay? It's a special case of this. If the base is e, then the way this would be written is natural log of e to the x equals x. Now, let's unpack that for a minute. I told you earlier in the lecture that when you see the natural log, what that means is it's a log base e. So do you see that this is the same as this property right here? It's just that we've written it in shorthand here, so it looks a little bit different, but the property still holds, and it's x. Okay, so these aren't actually additional properties that you have to memorize. I just want you to know that this actually applies for natural logs as well, and that can look a little bit different. The same thing happens here. This base can be e, and the log in the exponent can be a natural log, in which case the base on this natural log is matching with that e, and this gives you x. And similarly, for this one, the natural log of 1 equals 0, because that specific base is e. So these are really the ones that you want to memorize, and then as you get familiar with the shorthand for natural logs, those will follow quite naturally. Now, the homework problems using these properties are going to look like this. All right, and it's going to say simplify. Or in other words, reduce. So you're using these properties to reduce. So what is this looking like? Well, it kind of looks like this property right here, because I've got the log base 4 of something, but there's no power up here and these guys don't match. So what I have to do to reduce this is to make these guys match. And the way I do that is I want to write 64 as 4 to some power. Now, if I can't, then I can't reduce it. It's got to be a 4. And so then the question is, can you? 4 squared is 16, and 16 times 4 is 64. So this is going to be 4 cubed. Then I've created one of those properties. This cancels, and my answer is just going to be 3. Okay, a similar idea in another problem. Okay, I'll look at this and say, oh, these 3's are matching, but what's the power up here? This is where we remember that roots are actually powers. They're fractional powers. So the square root translates to a 1/2 power. And now these guys cancel, and I get 1/2. Okay. Let me do one more of these. All right, I have to ask myself, what's the base on this? Okay, that's a log base e, right? That's what that means. And so I just need to get this e up on ground level and with a power. So I need to move it up, and then hopefully that jogs your memory. Oh yeah, I can move things up on the fraction, but I do that by making the power negative. So it's a +1 down here. So when I move it upstairs, the power becomes a -1. And now these are ready to cancel, and I'm left with -1. Okay. All right, I think that is all that I have for you in this section, and I will see you for the next.